I'm Chris Laughlin, and today I'm going to be talking about the Immutable Way, a guide to cleaner, more predictable JavaScript. I'm going to be talking about all things immutability in the land of JavaScript. So first, who am I? I am a principal UI engineer at Rapid7. I'm also a freelance writer for SitePoint and LogRocket, and I also create educational, fun, JavaScript web-based technology videos on TikTok under the handle The Dyslexic Developer. So let's look at the definition of immutability. Immutability in program refers to data that cannot be changed after it's created. So when we think about immutability, we think about mutation. Mutation is the act of taking something and changing it over time so that the original item is now what the changed item is. So we lose that history and originality of what the original thing was. Whereas immutability is the act of changing something over time, but preserving what the original value was. So let's look at a more kind of relatable example of this. If we take the concept of a library book, so we can check out a library book, and then in this book we could make a doodle. So draw a little smiley face in that book. When we do that, we modify the original book because we've just checked out that book. There is no copy of that book. We've just modified the original book. That modification will live with that book forever. And we've also then lost the history of what was underneath that smiley face and what was there beforehand. So this is the concept of mutation. Then we can think about immutability using the same example of a library book. So we check out the book, but in this case then we make a copy. So say we scan it in and print out a copy of the book. So we've created a brand new book, but it's identical to our original book until we make our modification. So again, we draw a little smiley face in the book, but then when we look at our original, we can see that our original has not changed. It has stayed the same. It is the original history of what that book was because we made that copy. We took the original book, photocopied it, scanned it, whatever, printed out a new version, and now we can make modifications to this new version without making any changes to the original. And this is the concept of immutability. We're making new versions and our original is not being mutated. So how does this look in the world of JavaScript? So first off, we're creating a variable called name. So we're defining this and declaring it with a let. And let by nature is mutable and designed to be mutable for this reason. There is arguments between the use of let and const, but we'll touch upon those along the way. But in this case, we're just saying let name equals Chris. And when we log out name, it logs out Chris. Because let is mutable, we can make changes to it. So we can reassign the variable of let or name. So we can say name equals Christopher, so the long version of my name. And then we can do console.log name, and now we log out Christopher. So name is now Christopher, it is no longer Chris. So we've mutated the original value of name. Then we can have a look at a object, and this is being declared using a const. So this is starting to bring in some of the differences between const and let. Some people argue that they're the same and they should be treated the same. And by writing let, you're only having the type 3 characters compared to 4. But there is subtle differences that we'll kind of experience along the way. So we've created a constant variable called speaker, and we've assigned it 3 attributes. So we have name, location, and age, and that's obviously not my real age. So what if we want to reassign the speaker object like we reassigned the name? So now when we try and say speaker equals a new object, and this object only has name of Christopher, so the full name, we get a JavaScript error. This error is an uncaught syntax error saying speaker is read-only. So the JavaScript language itself is checking that you're making a reassignment to a constant variable. So anytime you want to reassign a const, it is going to throw an error and stop your application because consts cannot be reassigned. And this is by design. And when you define a const or use a const, this is by design. However, there's a difference to how const works in JavaScript compared to other languages that are out there. So we can make modifications to attributes on the const object. So we can say speaker.name equals Christopher. And then when we log speaker, we can see that name is now Christopher, location is Belfast, and age is 100. So the name attribute on the speaker has changed, but we didn't reassign the whole object, so JavaScript didn't complain. And this is where the concept or catches people out in JavaScript compared to other languages. I myself think of const as this object is not mutable. Even though you can mutate it, you should not mutate it. Like other languages treat the const keyword. But in JavaScript, it's treated differently. And this is where a lot of the complaints between a let and a const don't have much differences other than the reassignment issue, which could be caught with a linter or code checker. So how can we then handle immutability when it comes to constant variables? So this started again with our speaker object with name Chris, location Belfast, age 100. And then let's create a new constant variable called full name speaker. And we're going to use the ES6 spread operator to take our original speaker object and create a copy into our full name speaker. So the spread object was introduced in ECMAScript 6. And what this kind of does is takes an object and kind of explodes out its attributes and allows you to push them into a new object. So we've wrapped the spreaded speaker in curly brackets. So we're saying, here's a new object, take all the attributes and explode them out into this new object. And this is very useful for doing copies of objects, and especially because it is very dynamic. So we don't need to know all the attributes of the speaker. We can just say, create a new speaker from this previous speaker. This allows us then to say full name speaker.name equals Christopher. And then we can log out both of our speakers. So we can log out speaker, which is our original, and the name is still Chris, location is Belfast, age is 100. And in our new full name speaker, when we log that out, our name is now Christopher, location is Belfast, and age is 100. So we can see here that we were able to modify an attribute on our full name speaker and not make any changes to our original speaker object. And this is a very core basic example of immutability in JavaScript. We have taken an original object, kind of like we did with our library book. We've made a copy of it. So we've scanned it and reprinted it, and then we've made modifications, and we haven't affected or changed the original. The original is still our golden source of truth in our state, and we haven't made any changes to this. This is the very introduction, very beginning part of immutability in JavaScript. And the reason why I say introductory and beginning is in our next example, we can see where there is still pitfalls and issues with using spread operators to achieve immutability. So in this case, I call it attribute mutation. So again, we have our speaker object, but we've kind of modified it a little bit in this case. So we still have our name, but now our location is no longer just the string Belfast, it's an object. So it's a nested object on our speaker. And this object has two attributes, city, which is Belfast, and country, which is UK. And we still have my unbelievably old age. So we now modified our speaker to have a nested object inside of it, which is our location. So like in our previous example, we want to call the spread operator. So we do full name speaker equals empty object. Inside of that empty object, we call spread and then speaker. And then if we want to mutate a nested attribute, we can say full name speaker dot location dot city equals Derry. So we're changing the city on our location. Now on the right hand side, when we log out both our speaker and our full name speaker, we can see where we run into the issue. We still have name, which is Chris, in location, and our speaker is Derry. Country is UK, age 100. And on our full name speaker, name is Chris. On our location, our city is Derry, and our country is Derry. And we can see that the city on both of these objects are now the same. So we've gone a step back, where previously we used the spread operator to break apart an object and copy it into a new object, and then we can make modifications without any repercussions about going back to the original. But now we're having that issue where we are making changes to the original when we make changes to our copy. And this is due to how JavaScript handles copying, especially around the spread operator. The spread operator is a shadow copy. So when it comes to basic data types such as strings, numbers, booleans, it can easily copy these attributes across to the new object. When it comes to more complex nested values, such as objects, functions, promises, whenever we copy those across, they get copied by reference instead of copied by value, which means that the location in our full namespeaker is actually pointing to the memory allocated for this in our original speaker. So it's not a copy of the exact values, it's just copying our reference. That means when we make changes to our full name speaker, these changes are then reflected on the location of our original speaker because it's linked via memory. So how can we fix this issue? So as well, in the last couple of years, a new JavaScript API was added to the specification called structure clone. And this allows us to do full, deeply immutability modification in JavaScript. So again, we're starting off with our normal speaker object, name Chris, location is an object of city, Belfast, country, UK, and age 100. But now when we create our full name speaker, we no longer use the structure clone, we no longer use the spread operator that we did previously. We now use structure clone instead. So we call the structure clone function and we pass it the object that we want to clone. And the structure clone does a deep clone of all the values into the new object. So it's not doing that copy by reference, it's doing a copy by value. So then we can then call our modification again. So we can say full name speaker dot location dot city equals Derry. And then when we log out both of our speakers in the bottom half of the slide, we can see our original speaker stays the same, city is Belfast, and in our full name speaker, our city is now changed to Derry. So it hasn't copied back into the original, and we have full immutability, and we're able to make modifications to an object with deeply nested attributes and still hold the original source of truth in our state. So there are some built-in utility functions in the JavaScript specification to help with immutability. And the great thing about these being built into the language itself is they'll exist across different runtimes and they're fully standardized. So they should exist in all browsers, Node, Bun, and any kind of serverless architecture that you may run into. So the first one we're going to look at is the object.freeze method. So these have been around for a long time and I rarely see them actually being used in practice, but they can be very useful. So again, as our previous examples, we have our speaker const, name, location, age, and then we call object.freeze on it. And what this is doing is it's freezing any modifications to this object. So then if we try and do something that we've previously been able to do, which is part of the spec and it is allowed, we can call speaker.name equals Christopher. But now we get a on-call type error, cannot assign to a read-only property. So we've now made all the attributes on our speaker read-only, and we cannot make any modifications. This is very useful if you wanted to completely lock down a constant variable. As we talked about in the past, you cannot reassign the value of a constant because the JavaScript language will throw an error and stop. But you can reassign attributes on this. And if you're thinking in the way that I think, that constants are always non-mutable and they should never change, but the language still allows it, you may want to put checks and balances in place to prevent these modifications from happening. Say if you were passing speaker to a function and then pass it to another function, someone might not know the speaker was a const and may try and make modifications to it if they're not following the immutable best practices. So calling object.freeze completely prevents this and means that the application will stop and completely error out. The next one we can look at is object.seal. So again, we have our speaker object, name, location, age, and then we call object.seal and we pass in our speaker object. So seal works a little bit differently from freeze. What seal does is it says anything that existed on this object previous to being sealed can be modified, but any additions after the fact is completely prohibited. So you're no longer allowed to add any additional attributes to the object, but you can still modify attributes on this. So this can be useful for different edge cases and different use cases, but we can see here in an example, we can call object.seal and provide it our speaker. Then we can say speaker.name equals Christopher, and when we log that out, that will log out Christopher because we can make modifications to the object. But if we then wanted to say speaker.occupation equals software engineer, This will then throw a type error, so you cannot allow property occupation to object. It's not extensible. So what we've done is we've locked down our constant that it cannot be added to in the future. So two different approaches of handling immutability natively in the JavaScript language, but these checks can easily kind of prevent edge cases, bugs, issues later on in your code. So let's take a look at a real world example. So we have the Immutable Wares site where items never change, and thanks to the powers of AI for generating a shopping application for me and putting puns in. So we have a shopping application where we have different wearables, items, and this is just a Vite client-side application built in React. And we can see when we start adding this overly priced backpack, reasonably priced shirt, reasonably priced jacket, they get added to our shopping cart, and we can see the items being added in. We have our prices, we can remove them, and we have a total of our running, like all the items in our basket, how much we're totally paying for this. So say I wanted to make a change to our application and I wanted to add in some currency symbols. So I wanted to add in the pound symbol to show that this is all a British website that's selling in British pounds. I can jump over to the code, and I have this products component. So again, this is React application. So we have a product component, and this takes in a list of their products, and we are mapping over our products and rendering out divs for each of these products. So if I wanted to do the bad way of handling this, and I wanted to add the pound symbol to the start of every price, I could iterate over all the products before rendering and say for every product, update the value. So override the value of price. So say product.price equals a templated string. And at the start of that template string, it's the pound symbol. And then we can make a save here and refresh our application. And we can see this achieved what we needed. We now have pound symbols in front of all the prices on our products. So let's again verify our changes haven't broken anything else by adding some items to our cart. So our overly priced backpack, reasonably priced shirt, reasonably priced jacket. And we can kind of see there's some issues happening in our application. Why do we have multiple pound symbols in front of each of these prices? This is also in our basket. And why is our total now looking like we're concatenating strings together instead of actually totaling numbers? So we can see that there's an issue being caused here. And we're going to assume that this is an immutable issue. So the main issue here is we're taking our products rate, which is our golden source of truth, our state of all of our products, and we're iterating over it using the for each iterator. And then for each of the products, we're updating what that product price value is. So every time this component re-renders, it's going to run this for each, and it's going to reassign the value to be whatever it currently is, but with a pound symbol at the start. So we can see based on how many pound symbols we have, that's how many renders there's been triggered. So we've had 4 renders for each of these pound symbols, and then we're putting that into the DOM. So this is obviously the wrong way to make changes to our data for display purposes. So we can comment this back out, and then we can do the real proper way of doing this. So instead of making modifications to the data, we make modifications to the DOM or the JSX that we're rendering in our application. So we can comment out how we were rendering price before, and then uncomment what we want to do. So now we're putting the pound symbol into the actual markup and rendering it that way. So the price doesn't actually change. We're not modifying our data. We're keeping our data as our source of truth. Now we could do this as well where we could say, create a new constant called display products and map over it and modify it that way. So we're not modifying the original products, and we could use our structured clone as well to handle this. But in this case, we don't need to do that. We don't need to make any kind of loops and iterations. We can just say, put a pound symbol in the DOM before the price. So let's refresh, and we still have achieved what we needed to achieve. We have our pound symbols for each of our items. And then let's start adding our overly priced backpack, our reasonably priced shirt, and our reasonably priced jacket. And we can see they're all updating, and we have our total calculating. Now we could go in and then update our shopping cart to say add in the pound symbol before each of these, and again for their total as well. But we've prevented that immutability issue that we were having before. And imagine you're working not in just a very simplistic product like this, but you're working in a large application where potentially products is being passed into multiple different places. You might make a change, but not realize how that ripples down your application. And because of the way this works by modifying the original data, it's going to triple up and down your React tree. So making modifications to the data can lead to really bad, really interestingly difficult to debug issues, especially for you and for your coworkers. And it's very heavily encouraged when, especially building React applications, to follow the guiding principles of immutability and make things immutable to prevent these kind of issues. So as we kind of seen, one of the main error-prone places it comes to when we think about immutability is when we're working with arrays. Because when we're building applications, everything's just arrays of data. And we're mapping, modifying, doing something with that data. And arrays have multiple different methods that allows us to interact with them. Here's just a handful of them. So we have for each, which we've already seen used. There's the filter, there's the pop, push, map, slice, reduce, sort, and so on. There's many more. Some of these are mutating methods. Some of these are immutable. So let's take a look at an example, a very basic example, working with arrays and how immutability can catch us out. So in this case, we have a shopping list. So we just have the name, milk, eggs, and bread, and how many quantity that we have for these. And then we have a sort function. So we want to click a button to sort a shopping list alphabetically. So we can call shopping list.sort and take in the A and B, and then log out, do our comparison. And then when we call the render function, this just redraws the DOM with our new shopping list. So our sort function is mutable, so it's going to mutate our original array. And when we run this in our application, we click sort, sorts it alphabetically, but then if we wanted to have an unsort button, there's no way of knowing what our original order was. We don't know what our original array looks like anymore because we've modified what that array is. It's no longer in the original order that we got. So we've lost that source of truth. We've lost that history of what our data is. So how can we fix this? Because this is a very simplistic object in each of our items, we can use the spread operator. So we don't have to go down the structure clone approach. We can just say sorted list equals our current shopping list spread into it. So we're making a shallow copy because they're just simplistic name and quantity. There's no nested attributes. We don't have to worry about copy by reference. It'll just copy those basic values across. And then on our sorted list, we call our sort function. So now we're creating a new array. We're sorting that array, and then we're setting that into our value that we're using to render the DOM. So now we have the ability, if we wanted to, then create a unsort function that would return it back to what the original value was. So as part of this as well, immutability is becoming more and more encouraged in JavaScript, to the point where the ES 2023 spec released a number of array methods that encourage and use immutability compared to some of the methods we've just looked at that were mutable by default. So let's take a look at the first one here. So for each of these, there's the original and then the new immutable version. So we have the reverse method versus the to reversed, and you'll see that there's a pattern of how these are being named. So the new immutable one will be to, and then whatever it is, ed. So we're reversing something and then we're to reversing, so we're returning something that has been reversed. So if we take the example where we have an array of messages, so these have the sender, the text, the timestamp, and if we call messages.reverse and we iterate over our messages, we see that they've been outputted in reverse order. But again, off our kind of shopping list example, we've lost the original history of what that was. We don't know what that original array of messages were, so we can't sort them, and maybe we could try and sort them timestamps, but it wasn't the order that we were given them. So we want to then use the to reverse method, and we can just call reverse messages. So create a new const that's going to hold the array of our reverse messages, and then call messages.toReverse. So in this case, we don't need to do the spread operator. We don't need to do a structure clone. The to reversed will return that new array of messages for us, reversed as well. So then, like we did previously, we can just for each over them, and then we can log them, and as well, we can log what our original messages are to see if they actually did modify. So the first part is each of them in the reverse order, and then when we log out that original array, they're in the order that was given us. So we can prove that we haven't modified the original array. The next one we have is the sort function. So we looked at an example with the sort function in our shopping list, or And we can see that we have a two-sorted method that complements this. So originally we would have done products.sort, and that would have mutated the original array. Now we can create a new sorted products constant and then call products to sorted, and that's going to sort the products and return that newly sorted array back to us, but not modify the original. And then we can log these out. We can see the ones that are sorted by price and then the ones in the original order. So we're not modifying that original array. And then lastly, we have the splice method. So the splice method is very useful for kind of cutting up, removing items from arrays, replacing items in place in arrays. And now we have the to spliced method. So we can call new cart and we can do cart items dot to splice. And this operation is removing the second item from the array. And then say if we wanted to remove the last two items, we can call cart items again. And notice that we can call cart items each of these times, because it's not being modified by the spliced operation. We're still holding the original, so we can potentially have multiple representations of the original array without having to create copies or modify the original array. We're just using the built-in methods to return the new version of that array. So we can say cart items splice -2, so we want to remove the last two items. And then lastly, an example where we can then update the items. So we can say to spliced, we want to update the third item, and then pass in what the new item is. When we log these out, we can kind of see what the results look like. So we can say our first one is we wanted to remove the second item. So we now only have 3 items in our list. Our second one is we were removing the last 2 items. So now we only have 2 items in our list. Our third case was we wanted to update the third item. So when we jump to that, we can see that the third item now has updated the new item. And then lastly, we log out our original cart items. We can see our original cart items has not been modified, as it stayed the exact same throughout the entire process. So we've used immutability to make modifications to this using a native built-in function, which again is compliant and spec'd across all runtimes and all browsers. So we don't want to just stop there. Like, the language has provided us recently some immutable functions, but there has been immutable libraries out there like pushing the concept of immutability and the benefits of immutability. So the two kind of key players is Immutable, which gives you different utilities and functions to interact with data structures in an immutable way. And very similar as well, that there's a library Immer, which does the same kind of concept. It allows you to interact with different data structures in an immutable way. So you're not restricted by the only things that you're provided from the language. You can also use different libraries and utilities that will handle different edge cases and maybe handle them in a more smooth and interactive way. And the hopeful goal is the more people get into immutability, the more these libraries will kind of feed back into the spec, and we will no longer have to rely on third-party dependencies. We will have things that are compliant and spec'd and supported across all browsers, all runtimes. So in conclusion, we've kind of covered all the different ways of immutability, why immutability is important, real life examples of immutability in the wild, bugs that can be caused by it, how we can solve those bugs, the way that the language is leaning towards immutability in general for JavaScript as a whole, and some kind of third-party libraries that you might want to delve into if you want to get more deeper into immutability. So I just want to say thank you, and hopefully you go off and enjoy immutability and start building immutable applications.